Hello and welcome to our lesson on polynomial functions and models. This is going to be from section 8.1 in our text. We are going to cover everything polynomial in this section, including the degree, the leading term, leading coefficient, the end behavior, and the multiplicity test for the roots. We got a lot of stuff to get through. Let's go ahead and get started. First, we have this grid that we're going to fill in. And as we populate the grid, we're going to be teaching you some concepts. So, starting with our first example, we have f of x equals 3. Now, the classification is going to be what we call that particular polynomial function. If f of x is 3, which is a number with no variable attached, the classification is constant. So we call that a constant function. The degree of a constant function is 0. Now, for a little more detail, remember I said that there is no variable? Technically, there is an x there. It is x to the 0 power. Because anything to the 0 power is 1, that would really represent 3 times 1, which is 3. So the degree is going to be the biggest power on any variable. For the entire polynomial, whichever variable has the biggest power, that's going to be your degree. The number of terms in this function is 1. There is only one term, the 3. The leading term, since that is the only term, then 3 would be the leading term. And the coefficient is the number in front of the variable. So since there is really an x there, it's x to the 0, the coefficient would be 3. Next, f of x equals 3x minus 5. Now this function is linear. That is the classification, linear. If you look at this, you could imagine that this is y equals mx plus b. F of x is y, so this is really slope-intercept form, where the biggest exponent is 1. So the degree of this polynomial function is 1. The number of terms, this time this function has 2 terms. The leading term is the term with the biggest power. So the 3x is the leading term. Notice that all of it is the term. The number, the variable, the exponent, all of that consists of the term. And the leading coefficient is always the number in front of the leading term. So in this case would also be 3. Next function is quadratic. So when you have an exponent of 2 as your biggest power, we call that a quadratic function. The degree would be 2, since 2 is the biggest exponent on any variable. This particular polynomial function has 3 terms. Again, the leading term is the term with the biggest power, so the 4x squared would be the leading term, and the leading coefficient would be the 4, the number in front of that term. All right, next, x to the third. If 3 is your biggest power, we call that cubic. That is a cubic function. Again, the degree is the biggest power, so the degree would be 3. 1, 2, 3, 4 terms. This has 4 terms, where the leading term is x to the third. And the number in front of that term, since there is no number visible, that is an understood 1. So the leading coefficient would be 1. All right, moving up the chain, x to the fourth. If your polynomial function has a degree of 4, where 4 is the biggest power, we call that a quartic function. The number of terms, 1, 2, 3. This only has 3 terms. Again, the leading term is the one with the biggest power, negative x to the fourth. And the leading coefficient this time would be negative 1. There's a negative 1 in front of the x to the fourth. 2 more to go. X to the 5th as the biggest power. That's a degree of 5. We call that quintic. That is a quintic function. This particular polynomial function has 3 terms. The leading term, 7x to the 5th, and the leading coefficient is 7. And lastly, for my favorite polynomial function of all time, the classification of a 6th degree polynomial. I'm not even joking. That is a sextic. That is a sextic function. You can Google that if you want, but that is the official math term for a 6th degree polynomial function. Sextic. Number of terms, 3 terms. Leading term is the negative 3x to the 6th, and the leading coefficient this time is negative 3. So that covers all of the polynomial classifications that you're going to need to be aware of. How to determine the degree of a polynomial, the number of terms, the leading term. Remember, the leading term is the one that the degree came from, and the leading coefficient is the number in front of the leading term. Next, we need to talk about the leading term test that determines the end behavior of the graph. Whether your degree is even or odd, and whether the leading term is negative or positive. Based on those 2 criteria, you can determine the end behavior of your graph. And I'm going to use Desmos to go through every one of these scenarios to show you what we're talking about when we say end behavior of the graph. I've got 1, 2, 3, 4 functions because we've got 4 possible outcomes. So remember, the degree is the biggest exponent on any variable, and the leading term is the term that the degree came from. So we want to look at the first scenario first. Even degree, positive lead term, and that says that the graph rises left and right. Now, what does that mean? Well, here we have a function that has an even degree. The biggest exponent is a 2, which is an even number. And the leading term, which this is the only term, so it's the leading term, is positive. So if you look at this function, you're going to see as I scroll out and move the graph that this graph rises left and right. No matter how far I zoom out, what we mean by end behavior is what the graph does out on the ends, like out on the edges of town. This graph is going to rise left and right forever. And that's with an even degree and a positive lead coefficient. Now, if I could reset this, let's go back to our notes. And what about if we have an even degree with a negative lead term? That says it should fall left and right. So here we have negative x squared, again an even degree. This time the leading term is negative, and you can see that this graph falls left and right. No matter how far I zoom out, it's going to go down on the outside of town. Okay, it's going to fall left and right. And so next we're going to look at an odd degree with a positive lead term. Odd degree, positive lead term, should rise right and fall left. So if I turn that on and recenter my graph, you're going to see that this graph rises right and falls left. That's with an odd degree and a positive lead term. Again, all this does is it determines the end behavior, what the graph is going to do away from the center of the action, okay? What it does is you go to the right forever and to the left forever. And last but not least, we have an odd degree with a negative lead term, rises left, falls right. And so here we have an example of that. A negative lead term with an odd degree. And again, you can see as I scroll out, that it's going to rise to the left and fall to the right. So that's what you're going to have to know for this particular part of the lesson, is how to determine the end behavior of the graph. Now, the symbolic representation, what you can do, instead of having to write the words rises left and right, you can just simply make symbols like this: rises left and right, falls left and right, rises right, falls left, rises left, falls right. You can also use this notation to indicate the end behavior of your graph. All right, so we're going to look at number 19 from section 8.1. This would be like an example of maybe a homework or a test question where the instructions would say, determine the end behavior of the function. And again, to do that, the first thing you look for is the degree. You want to know if it's even or odd, okay? So the degree is the biggest exponent on any variable. 6 is even. So we now know that it has to be one of the first two options. And then we want to know, is the leading term positive or negative? Well, this is the leading term, and it is definitely negative. And so that means that our end behavior is going to fall left and right. And again, you can either use the symbolic representation for that, or you can write the words falls left and right. But that's how that particular problem is worked out. And the last thing we want to look at in this lesson is even odd multiplicity. Now, what the multiplicity does is it determines the behavior of the x-intercepts. So when you're looking at the graph of a function, some graphs come in and touch the x-axis. Those are called x-intercepts. They're also called zeros or roots, either one of those terms. If you know the multiplicity of those roots, of those x-intercepts, then you can determine the behavior of the graph at the x-intercepts. So for example, I've got Desmos handy here, and I have a couple of functions typed in. What we're going to do is we're going to look at the graph of the function and explain how the multiplicity determines the behavior of the x-intercepts. So this first function that I'm going to turn on, once I zoom to a standard window, is already factored. Notice that this function is in factored form, and so to get the x-intercepts, you would set each factor equal to 0 and solve. So there will be an x-intercept at 0, at positive 1, and negative 4. The multiplicity corresponds to the exponent of the factor. So for this factor of x here, since it has an odd power, an odd multiplicity means that it's going to touch and cross at that x-intercept. So if I go to the x-intercept of 0 and zoom in there, you're going to see that at that x-intercept, the graph comes up, it touches, and then it crosses over. So if you have an odd multiplicity, remember the multiplicity corresponds to the exponent of the factor, that indicates the graph will touch and cross. It's going to go from being on the negative y values, it's going to cross and then be in the positive y values. The next x-intercept is 1. 1 minus 1 is 0. That's a 0 of the function. And it has an even multiplicity. 2 is an even number. And so if you have an even multiplicity, your graph should touch and turn. Now, what does that mean? Well, let's go to 1 on the x-axis for that 0, for that root. Since our multiplicity is even, what the graph is going to do is it's going to come in, it's going to touch and turn. It bounces off. It does like a ricochet. It comes in, bam, touch and turn. It doesn't cross over into the negative side. So again, an odd multiplicity does a touch and cross, touches and crosses, but an even multiplicity does a touch and turn. It just touches the x-axis and turns right around. And let's go ahead and look at the other x-intercept. -4 would be the other x-intercept. The multiplicity corresponds to the power. The understood exponent here is 1, which is odd. So if we go to -4, we can see that the graph does a touch and cross. Odd multiplicity, touch and cross. So again, the only thing that the multiplicity determines is what the graph does at that x-intercept. It's either going to touch it and cross over, or like at 1 here, it's going to come in and touch and turn around. Now we're going to look at number 39 here as an example of maybe a homework or a test question where the instructions would say, find the zeros of the polynomial function and state the multiplicity of each. So this function is not factored. If we're going to find the zeros, we need to factor it if at all possible. So since this function is a cubic and it has 4 terms, we're going to try factor by grouping. So we're going to group the first 2 terms and factor out the GCF, which is x squared. And we're going to group the last 2 terms and factor out the GCF, which is -1. And if that was like, whoa, what just happened? You might want to go back and review my lesson on factoring. Now, we're not done. The next step is that we need to factor out the common factor of x plus 3. And factoring out the x plus 3 leaves me with x squared minus 1, which is the difference of squares and can factor further. So x plus 3 comes down, x squared minus 1, difference of 2 squares has different signs. And if we fill in the blanks, we get x's and 1's. So now that this is factored completely, I can now set each factor equal to 0 and solve. So we get x is -3, x is -1, and x is 1. And if you're going, well, wait, you skipped the step, you didn't actually show setting it equal to 0 and solving. Well, okay, there's a shortcut there. If you plug in a 1, say here, 1 minus 1 is 0. So whatever number makes that 0 is going to be your solution. These solutions are your x-intercepts. So remember I said that the multiplicity corresponds to the exponent of the factor. There are 3 factors here, and they all have an exponent of 1. So therefore, every one of these x-intercepts is going to have an odd multiplicity. And an odd multiplicity means that at every x-intercept, the graph will touch and cross over. And I can illustrate that. I've already got this typed into Desmos. If I turn that on and click on every one of the x-intercepts, first of all, that does verify my handwritten work. -3, -1, and 1. -3, -1, and 1 are the x-intercepts. Notice that every x-intercept, we do a touch and cross. Touch and cross, touch and cross. Every x-intercept touches and crosses over. Now, just to go a step beyond, because I like to give as much instruction as I can, in order to graph these polynomial functions accurately, you really need to have the x-intercepts. It's nice if you can determine the end behavior so you know whether it's going to rise right, falls left, or whatever. But the other characteristics that you need to know how high does this hill go and how low does this valley go. And notice the y-intercept is also a nice characteristic. As far as the high point and the low point, really to get those efficiently, you need calculus. You need a concept called the derivative. Finding the first derivative of the function can get you what we call the maximum and minimum value. There is also a point in here where this graph goes from being concave down to concave up. Notice this graph is cupped down here. It makes an upside down cup, but over here it's cupped up. And so there's a point somewhere in here where it goes from being cupped down to cupped up. And that point is called an inflection point. And to find that, you really need calculus, the concept of the second derivative, which is where you get inflection points. So there are things that you can find about a polynomial function that are beyond what we talk about in algebra. All right, so one other thing I might mention before I move on. Once you factor your function and you come up with your multiplicities, it's nice to notice that the exponents on your factors, if they don't add up to make the degree, you made a mistake. So if you add all your multiplicities, it should equal the degree of your polynomial. And the degree and the leading term, remember, if they're negative or positive, those two characteristics can determine the end behavior. So again, an odd degree with a positive lead coefficient, odd positive, that's going to rise right, fall left. And so there's your notation you can use for that. Rises right, falls left, which we can verify from our graph here. Rises right, falls left. And I think that's going to do it for this particular lesson. So if you have any questions or comments about anything that I've covered, please feel free to leave those in the comment section below, or you can text me. And thanks for watching.